Okay, so this is solubility product, KSP. We've already looked at precipitation reactions, some interesting ones, and we've talked about the importance of precipitation reaction, whether it's in nature, the production of the hard shell of a bird egg is solubility product application, just classic, stalactites, stalagmites. So it's interesting and important. Anyway, let's take a look. One of the reactions we did, we had aqueous silver nitrate. We had aqueous sodium chloride, aqueous. Notice, let's just pretend that we've got 100 mils, and the solutions are 0.10 of each. And what we're going to do is combine these aqueous solution. Notice the hydrated ions that are hydrated by the water. And then let's look at our product here. So according to the solubility rules, this has to be aqueous. Sodium nitrate. Nitrates are always soluble. Sodium, potassium, lithium ions are always soluble. So these are going to be our spectator ions. Notice there's our precipitate right there. Precip. And if we combine these two, be careful, we're combining, so molarity is changing because excuse me, molarity is changing because we're changing the volume. So let's just take a look here. We've got 200.0 mils now. And notice what you're going to see is solid precipitate produced at the bottom. So that's AgCl solid. Okay? Here's the aqueous water. Don't forget, these spectator ions are still present and are floating around as aqueous anions and cations. So these are spectator ions, and they're present in significant quantities. If this is 0.10, then for the sodium chloride, then of course the Na positive, due to the ionization as a 1 to 1 to 1, Na positive is going to be 0.10 molarity at the start, but then it's changing because now we've changed the volume. We won't worry about that right now, though. Let's get the idea of slightly soluble. So notice, here's the silver chloride. What's going to happen is this will immediately form equilibrium with Ag positive plus Cl minus. And these would be in aqueous amounts. So, floating around along with the spectator ions, sodium spectator ion nitrates, we're going to have small amounts of Ag positive and Cl minus. When I say small, once again, I don't mean insignificant. Small amounts of heavy metals in solutions can have a toxic effect on living organisms. For example, we could have if lead levels get to about 0.65 parts per million, if I'm not mistaken, 0.65 parts per million lead in the blood, that leads to brain damage. So think about that, 0.65, so 0.65 grams of lead per million grams of blood. That's not a lot, but it can have profound effects. So just kind of keep that in mind. Anyway, let's see what we got here. All right. Let's rewrite this as an equilibrium situation. So I'm going to rewrite this as equilibrium. I'm going to clean this up a little bit. And let's just worry about the solubility here of the AgCl. Let's rewrite this in a more traditional form now. So here's my solid AgCl. We're going to have an equilibrium with Ag positive aqueous plus Cl minus aqueous. All right, now, since we have an equilibrium situation, this is going to be a K value. But since we're dealing with solubility of these slightly soluble precipitates, and you'll see in a moment why we call it the solubility product. But let's call this KSP, solubility product. Let's write the KSP expression. So, KSP equals concentration Ag positive times concentration Cl minus aqueous. Notice here, solubility product, I take the amount of the molarity of Cl minus, times it by the molarity here, and that gets me my KSP value. The KSP value, if you had to guess, you'd say, okay, slightly soluble. It's got to be small. It's got to be really small. Typically, these are going to be smaller than Ka values, for example, typically. Anyway, this value is 1.6 times 10 to the negative 10th, I believe. So, there we go. Now notice what we can do with this, and actually before I go on, let me state this. We've talked about saturated, supersaturated, unsaturated solutions. So, saturated solutions have the maximum amount of solute that can dissolve in a given amount of solvent under the given conditions of temperature. So the maximum amount of solute that can dissolve in a given amount of solvent under the temperature conditions. Supersaturated is more than the maximum amount that can actually dissolve. Now, if that doesn't make sense, maybe if I find some time, which right now I can't find a thing at all, actually, because it's chaos going on in my life, but if I find some time, I can demonstrate a supersaturated solution, which is interesting, and I'll try to do that. Unsaturated solutions have less than the maximum amount of solute that can dissolve in a given amount of solvent, okay? That being said, if you take this as a whole, including the solid, let's call the whole thing supersaturated. There's more that can actually dissolve, and that's why there's a precipitate. But if you just consider the watery portion, this aqueous portion, and let's say that we're at 25.0 degrees C, because we're assuming all these Kas and KSP numbers, all of them are assuming, at least most of them, are assuming 25 degrees Celsius. So, if you're just considering the aqueous, this is saturated. It has the max amount of these two ions that can dissolve under the given set of temperature conditions. So this is saturated here. The whole thing we can call supersaturated, more than can actually dissolve in the water. And again, that's why the precipitate is there. So let's say I wanted you to tell me the concentration of silver ions in this saturated solution. So the concentration of silver ions in this saturated solution. Well, let's take a look here. Here's the KSP. Here's our KSP expression. Obviously, it's been a while since we've eliminated solids from K values, but remember, we eliminate liquids, we eliminate solids. Okay? They change, the amount of solid is changing, but it's minuscule, so the change is negligible. Anyway, let's figure out, I want your turn, let's figure out the concentration of Ag positive in this saturated solution here. So what is the concentration in moles per liter? Give it a shot. All right, here's my equilibrium expression again. So rewrite this. So there's my equilibrium expression. This is a solid. Let's see here. We can treat this question like it's an ice problem. Proud, I'm very proud. Let's go ahead and write ice here. And notice, since this is a solid, we don't have to concern ourselves with that. Again, this tiny bit of change that's from the ionization is small, so this essentially is not changing. The amount's not changing. So we're just going to concern about ourselves with these ions. Well, let's see here. So initially, before equilibrium, we're going to have 0 and 0. This is going to slightly ionize, so we're moving to the right-hand side there. And this is going to change by plus S. We typically use X, but for solubility product, we're going to use S. And S stands for the solubility in moles per liter. Notice S here as well. So at equilibrium, we're going to have S and S. Now let's go back to the equilibrium expression, which is here, and let's simply plug in S. So we have S, and I want U to determine the solubility of silver ion in that solution. So how much of this ion is dissolved in solution under these sets of conditions? It looks like, notice the math is pretty straightforward here. It looks like there is 1.26 times 10 to the negative fifth moles per liter of silver ions floating around in that solution. Notice there's an equal amount, because S is the same for both, notice there's an equal amount of chloride ions floating around. All right. What if we have a different situation? What if we have, let's take for example the lead 2 nitrate. So lead 2 nitrate. Let's that cool precipitation reaction that we looked at, where you get the yellowish lead iodide, lead 2 iodide precipitate. How does that look? Well, let's rewrite this in KSP form. So let's rewrite this. This would be KSP form here. So in other words, I'm not going to go through the net ionic and the molecular equation and so on. Let's get to the important stuff here. We've got lead iodide solid, lead 2 iodide solid, and that's going to ionize ever so slightly to lead ions plus 2I minus, aqueous. Let's say that we have a saturated solution. of lead iodide solid. So what is the concentration of the lead ions? What is the concentration of the iodide ions in that saturated solution? So, give it a shot. Notice, you're going to start by writing your KSP expression. And while you're doing that, I'll give you the KSP value. So there's the KSP value. Let's assume that, again, these are aqueous solutions. Let's assume the temperature is 25 degrees. KSP will change if, of course, temperature changes. So, continue on. Don't tell me a low battery signal just came up over that whole thing. Ugh. So lead-2 iodide. Let's do an ice problem. And we can eliminate the solid from our equilibrium. And let's start with 0, 0. We're going to move to the right here, so we're going to produce plus S, and this will be plus 2S. Let's then look at there's our equilibrium situations. Let's write the KSP expression now for this reaction. So the KSP expression, here's the KSP value, but we want the KSP expression. So we need both, but here you go. And let's look at the KSP expression. The KSP expression is going to be lead double positive. But now don't forget, we got to use these law of mass action. We have to use the stoichiometric coefficient. So now, it's been a while since we've done this. With acids and bases, the stoichiometry was most of the time, if not all the time, was a 1-to-1-to-1 relationship. But now it's a 1-to-2 relationship. So we need to take this I minus, and we need to square that. So here is the KSP expression. Again, if I ask for the KSP expression, simple. If I ask for a value, you're obviously going to give me a number value. Now notice, just to review, that number is not, has no units. Hold on a sec. All right, so notice at equilibrium, we've got S and we have 2S. Let's plug these into the right spots here. So notice lead double positive is S, so that's going to be S. Notice 2S is that would be the solubility of the I minus. So we have 2S here, but don't forget to square that. Now, if you do the math here, we take 2S and square it, so then we're going to have 4S squared times S, so that equals 4S cubed equals KSP equals 1.4 times 10 to the negative 8th. Notice, I'll give you a moment here to digest that. It's not really anything new per se. I'm going to get rid of this last problem. And we're not dealing with this reaction anymore, so just kind of clean house a little bit. Look at how useful that is. Whenever one of these precipitates ionizes in a 1 to 2 fashion, it'll take on this form. So KSP will always equal 4S cubed, assuming that it's 1 to 2. For that matter, didn't we see KSP equals Ag positive Cl minus for silver chloride? That was the KSP expression. And didn't we see that this was S and that was S, and there's KSP, so that equals S squared. So notice you can use this simple formula here, plug in the KSP, and then solve for S for any precipitate in a saturated solution, aqueous saturated solution, that it's got to ionize in a 1-to-1 relationship. And if it ionizes in a 1 to 2, notice this is awfully handy. Go ahead now and solve for S first of all. Solve for S. Well, here we go. 1.4 times 10 to the negative 8 equals 4S cubed. So let's go 1.4 times 10 to the negative 8. Let's solve for S. So we'll divide by 4. Doing this quickly. Take the cubed root here. That gives me S. So let's see what we got there. And I'll do the same. Remember, you calculator people, cubed root. So you got to figure that out with your calculator. It's usually going to be a second function. So I did this quick. Let's see what we got here. 1.5 times 10 to the negative third, it looks like, as my S. Now what that's going to equal is going to be the Pb double positive concentration in moles per liter. So that's Pb double positive concentration in moles per liter. What is the concentration of the I minus? It is simply 2S. So let's go 2S. 2S equals the I minus. So we got 1.5 times 10 to the negative third times 2 and that's going to equal 3.0 times 10 to the negative third big M. Didn't need a calculator for that, but I used it anyway. So this is my I minus concentration. Again, it's equal to 2s. Why 2s? Because of the stoichiometry. Just be systematic when you're doing this. All right. What if we had ionizations that were different than 1 to 2? What if we have 2 to 1? Doesn't make any difference, 2 to 1. You still can use this simple, where is it? You still can use this simple form of KSP equals 4s cubed. What about other types of ionizations? What about a 3 to 2 or a 1 to 3? Very handy. Very, very handy. In your book, this is page 747 at the bottom. Notice it's table 16.3. We've got silver chloride, KSP equals S squared. So we've got that for silver chloride. Barium sulfate ionizes 1 to 1, so KSP equals S squared. Lead fluoride. Lead fluoride follows this same pattern here. So this is F now, and this is F minus. So notice, you can use these, just memorize these handy little formulas. Notice if you have a 1 to 2 ionization, you're going to have KSP equals S. One more time, just for review, then 2S. Then we'll square that, and that's 4s cubed equals KSP. Notice this follows that pattern of 1 to 2. So we can simply solve for S. If we're given the KSP, we can simply solve for S. And then don't forget, you might be looking for lead, or you might be looking for the concentration of fluoride. So you got to adjust for the stoichiometric coefficient due to the ionization. What else do we have? So you've got your book there. Let's see. Oh, there's aluminum hydroxide, so that ionizes in a 1 to 3, and there you have KSP equals 27s to the 4th. What if you have a 3 to 2 ionization, 3 to 2, then you have KSP equals 108s to the 5th. Most of the time we don't deal with 3 to 2 ionization, but it could happen. And if you plug in, if you set up your ICE problem and then set it equal to KSP, and you do some fairly simple math, you don't even have to memorize those numbers for the 3 to 2 or the 3 to 1. But if you want to make sure you don't make a mistake, you're going to have to memorize those. Again, it's table 16.3. Relationship between KSP and molar solubility. All right, so there you have it. We've got more to do, and that's coming around in a moment.